Hey, what's up everyone? Today's video is an example of how to go from a brute force solution to the optimized solution. We are going to solve one of the most common coding interview question, two-sum. At the end of the video, I will tell you why this question is so frequently asked. Let's check the problem statement. We are given an array of integers, nums, and a target that is also an integer, and we want to find if there are two numbers that add up to the target, and if there exists a solution, then we need to return the indices of those two numbers. There will exactly be one solution, so we don't have to worry about the cases where there will be no solution or there are multiple solutions. So let's take a look at some example. Let's say the input array is 2, 7, 11 and 15 and the target is 18. In this case, the answer should be 1, 2 because 7 and 11 add up to 18 and they are at indices 1, 2 respectively. Now, in general, if we are to solve any problem manually, one simple technique that we can use is, of course, a brute force approach. We can pick the first number and try out all other numbers with that number. So 2 plus 7, then 2 plus 11 and 2 plus 15. If we still don't find the answer, then we can move our first number to the next index. So let's say now 7 is the first number and try out all other numbers. So 7 and 11, 7 and 15 and so on. We can try 11 and 15 finally. Now this solution will certainly give us the answer because we are going to try all possible pair of integers and there has to be some solution. So this solution works. However, there are going to be approximately n square number of pairs of integers and hence the time complexity of this solution is going to be big O n square. If you look closely, once we fix the first number, we are simply searching for the other number to meet the condition, and the condition is first number plus second number should be equal to the target. So essentially we are looking for second number, that is target minus the first number. So in this case, if the first number is 2, we are looking for 16 because 18 minus 2 is 16. But we can see that 16 doesn't exist, and hence we can move ahead and say fix the first number as 7. Now for 7 we will be looking for 11 in the remainder of the array, and in this case we will find that 11 exists in the array and hence the solution exists and solution is 1, 2. So this concludes that search is a critical operation in this solution. Now let's think of some ways in which we can improve the search time. In case of brute force solution, we were fixing one number and trying all others. Other numbers will be of the order of big O n, and there are n such numbers and hence the time complexity became big O n square. Now if we want to improve our solution, we have to reduce this search time from big O n. You can pause the video here and think about some ways of improving the search time from big O n. If your answer was to sort the array in the beginning, and then we can perform the binary search on the remainder of the array every single time, then that's one possible solution and that's a great solution. However, in this video we will look at another approach which is even better than the binary search approach, which will take big O n log n time. If your answer was to use a hash map or a hash set, that's great. A set or a map can search in constant time on average, and hence it's best way to solve this problem in terms of time complexity, because once we enter all numbers inside a set, hash set or a hash map, then the lookup is going to be big O 1 and hence we will be at most doing n lookups because there are n numbers in the array, and hence the time complexity in worst case would be big O n. We are still not sure whether we are going for hash set or hash map. The question asks for the indices of two numbers, and hence hash map is the right approach to go about it because we can map the number with its index, and that way we can get the index of the number. In the map we'll put 2 with index 0 and 7 with index 1, 11 with index 2 and 15 with index 3. And when we look for, let's say we are at 7, then we will be looking for 18 minus 7, that is 11. We will find 11 in the map at index 2, and in that case we will return 1 that is index of 7 that we are currently at, and 2 that we just found out from the map. Let's code the approach. As discussed, we will use the hash map, which is unordered map in C++. It goes from the integer value and we are mapping it to index, which is also an integer, let's say m. For each number, for int I equal to 0, let me take the size in a variable because we will need it in future. So I less than n and I plus plus. And for each number we are going to insert it into the map. So m of nums of I equals I. So nums of I is the key and I is the value. Okay, and now for each number, for int I equal to 0, I less than n and I plus plus. Int current number equals nums of I. Int other number, the number that we are looking for will be target minus current number. Now we will find this inside the map. So if map dot find other number not equal to end, map dot end, then we have found the solution. So we can return the current index I, comma the index of the other number, so other number. And if we don't find any solution, at the end we will return an empty vector. This won't happen because question guarantees that there will exactly be one solution. Although this solution works in most of the cases, it's not going to work in all cases. Let me give you a test case. So let's say the input array is 2, 7 and 11, and the number we are looking for is, let's say, 14. So when we are at index 1, we will find 7 will already be in the map. We will find that current number is 7 and the other number is 14 minus 7, that is 7 again. So, and we will find inside the map that 7 exists and we will return 1 comma 1. Now these are not two distinct integers, hence we will return the invalid output. To avoid this, we can simply add a condition that I should not be equal to m of other number. This should work perfectly. We can test it with a few test cases. One is already provided. The another one we just discussed is the same with target 18. We can run these two test cases and see what we get. Okay, so far it works. Let's try to see if there is a way we can improve our code. In the beginning is insert everything in the map. Because of that, we face a problem where I and m of other number can be equal. What if instead we insert inside the map after we have already checked whether the other number exists or not? So we don't insert in the beginning, but instead we look for the other number whether it exists in the map already, and then only insert the current number. So we will remove this, we will not put everything inside the map. We will look for the other number in the map. If we don't find it, that is when we are going to insert the current number. So current num equals I, and this takes care of m of other num to be not equal to I. So we can safely remove this condition and again run our code with the two test cases that we added. It's always a good idea to test with a few test cases before submitting. Okay, now we can submit the solution and see if it works in all cases. Great, it does work. Let's discuss time complexity one more time. So this is just a declaration, we can call it big O1. Here it's a one step. This loop will run n times, and the operation, this is big O1. This is again an assignment, just big O1. Now this is lookup inside the map, which is constant time on average. This is just returning a vector, and this is just again an assignment. So n times big O1 operation, and hence this is constant time, this is constant time, and this for loop will be big O(n). Hence the overall time complexity of our solution is big O(n). Talking about the space complexity, we are using extra map, which will have at most n number of key value pairs, and hence the space complexity is going to be big O(n). To solve this problem, we thought about the most basic brute force solution, which was trying out all possible pairs. Then we realized that search is a critical operation, and from there we found out the best data structure to perform faster searches. Here is the reason why this question is so frequently asked. There are multiple ways of solving this problem, as we discussed. One is brute force solution, another one is to sort the array in the beginning and perform the binary search, which will be big O n log n in total, and the last approach that we actually ended up implementing, which is big O n time complexity and big O n space complexity. Secondly, brute force solution is easy to come up with. So even if someone cannot optimize the solution, interviewer can still ask the candidate to code up the brute force solution to evaluate the coding abilities. Both these things can help in comparing two candidates more objectively. I'm going to post the link to the solution in the description below. You can also find some other relevant and helpful links, so check it out. In the next video, we will solve this problem with another approach that is more interesting and has different time and space trade-offs. If the array is sorted, we do not even have to use the hash map, and the problem can still be solved in linear time, that is big O n. We'll see that how. I'll post the video on Saturday. Subscribe to the channel and hit the bell icon so you don't miss that notification. Hey all, thanks for watching the video. If you enjoyed the process of learning how to solve this problem, give this video a thumbs up and share it. Post any questions in the comments below so either I or someone from the community can respond to it. See you next time and bye for now.